If you're on Twitch, say hello. I am watching the stream chat, and we're going to start off with Will talking about traceable collectives.
All right, so let me share my screen, and there's already an RFC, so that's mostly what I'll be talking through. There's also been a few design docs that are evolving. I'm going to try to make the RFC the source of truth. So the background is we want a way to trace and compile collectives, and we had some dispatch-bound collectives before, but they still had these process group objects and work objects that weren't really representable in our IR, and we wanted to fix that. So I won't go over all of the goals now, but most of them are basically getting them to be supported in a compiler, so we don't have to break graphs, and we can do larger graph stuff with collective ops in them. Okay, so I just made this into a picture. The orange boxes are the new stuff we're trying to build. There's kind of like two main layers. There's a dispatcher layer that represents collective ops and a wait op. And the wait op is a new thing we converged on recently, making that explicit so that the collective ops can be functional, but still asynchronous. So they return a tensor that isn't ready to be used yet. And you're not allowed to do anything with the tensor except look at its metadata. We are saying you are allowed to look at its metadata, like its size or stride or whatever. You're not allowed to peek at its storage. And then I think we're also saying you can chain these collectives together. You can do like an all reduce on top of an all reduce, and then finally a wait. But you have to call wait. Wait will synchronize. And so these are what show up in your graph.
Quick question, Will. Yeah, do you have to call wait, or is it more like Cuda, where if as long as you stay on the distributed side, things will change properly in the right order?
No, you do have to call wait.
Okay.
The exception is that you could probably I think we can allow that you can call multiple collective APIs in a stream without a wait in between, because we control the collectives and we can make sure that the streamed stuff works, but we don't control the streams. We don't control like the user's compute stream, and this also works on CPU. So
okay,
so the wait here is not per collective; it's like a global barrier.
The wait is a functional barrier that applies on a per collective basis. If you have you typically would call collective then wait, then collective then wait. The thing that I just said is a special case where, like, if you tried to use two collectives in a row on the same tensor, like if you tried to all reduce a tensor on some group and then I'll reduce that same tensor again on some other ranks, you could probably chain those together. That's what I'm saying, without a wait in between. Okay, so then that's the dispatcher API. So it's a pretty simple API. It also supports backwards and meta kernels, etc. There's a new Python API also sitting on top, the Traceable Collectives API, and it doesn't have the weight exposed. It hides the weight inside of an async tensor, which is a tensor subclass. So this lets users just call the all reduce and get a subclass back. And as soon as somebody tries to operate on the subclass, the weight will get called. And that's currently not traceable by Dynamo, but we have 3 different ideas about how to make it work in Dynamo, and we plan to do that. So this Traceable Collectives API is the new thing that should work in eager or compile, and it should have decent performance in eager, although it might still have an extra copy in eager. And dtensor API will be built entirely on top of Traceable Collectives. The way dtensor uses collectives today, it always allocates a buffer anyway before it calls a collective in place. So it's not going to get any worse in eager, and it will be great for compile. But we're not planning on updating Torch distributed APIs. So all the stuff that's built on top of torch.distributed, .allreduce, etc., will have to just be rewritten if they want it to be traceable. But it'll still be working. Like, this stuff won't go away. Oh yeah, one more thing is that there's like a desugaring layer for the traceable collectives front end. So the dispatcher level is always going to take a list of ranks and a stride, or a group size basically, to form a 2D matrix of what the ranks and groups are. And that's a little bit annoying, but it's good because you can trace without initializing a process group first. These are plain data types, and we can produce this format from like a variety of different front ends. So we can take a process group, we can take a device tensor mesh, or we can take the list events as a front end and just desugar it to this representation.
Natalia?
So isn't the group size the length of the ranks? What's the 2D matrix here that you've mentioned? Where are the
Right. So
two
we would
dimensions?
rather, yeah, we want to have a 2D, we want to have a list of lists of ranks because the op can have like, there can be situations where you have like two subgroups in an op. And so we can't represent that in current dispatcher because a code gen doesn't have a way to model, and we don't have a C++ type to target that's very obvious, like for a list of lists. So
yeah, but the API that you've written here is list of ints, not list of lists.
yeah, so we have a list of ints and a group size, and the group size is kind of like a stride. So that gives us the second dimension of our 2D matrix.
Oh, I see. What about the operations like all reduce and all gather, where you actually need to send the rank of this process to the API to know where to put the outputs or inputs? I don't see it as an argument in the dispatcher collector.
I think the idea is that the group, the ranks list will specify the ranks that are participating in the collective, and then the collective operation at runtime actually knows what its own rank is.
I see. Okay.
Albin?
My query was just about the eager APIs for Torch distributed. Any reason why you are saying these stay on the side and don't use these collective? Is it just we don't care enough to do that work, or is there some actual reasons why we cannot use these?
Yeah, it's mostly the former. I think we could update these if we were willing to make some changes, which might be BC breaking. Their APIs expose like work objects, which are kind of like futures, and also expose a front end that's based on a process group. I think we could definitely support the input side of those APIs, but making them return a work object seems hard. I think it's possible though. I think we could possibly update these things, or maybe we could add a mode, like a flag that if you use it in asynchronous mode only, it works, or something like that.
Okay. Okay, because then I'm curious, like, isn't one of the goals here, if we say that Traceable Collective supports compile, that we can then compile these eager constructs from distributed in an easier manner? Or is that a non-goal from this perspective?
Yeah, so in general, it would be really nice to make it so that existing distributed layers work with compilers, but I think, so dtensor is kind of a semi-existing layer. All the SPIMD stuff is built on top of it. It's going to work with compile and eager because of this. GDP doesn't even build on top of Torch distributed anyway. It's like built on C++, and DDP we're not sure we're going to update. I think it's probably easier just to make a new DDP that sits on top of traceable collectives than to update the one that's based on sort of optimizing eager. So if there's a value prop in making Torch distributed work traceably for some use case, maybe we'll consider it, but
okay.
I don't think so far people think that there is.
Okay, and just last one, is that true as well for the new composable FSDP, or like composable distributed APIs that were brought up this year? They fall also in that category or not?
Yeah, I don't know. I think it's a little unclear what to do with the FSDP APIs yet, but we will be supporting something like FSDP based on traceable collectives, just not clear how yet.
Okay, thank you.
So I just about used up 15 minutes. It's probably a good point to stop. There are some other details I could go into, but folks can look at this offline and put comments in.
Okay, any last questions? Okay, I want to pivot us over to Elias. Elias, tell us about Cuda graphs. What's going on with CUDA graphs?
Sure. So, should I just go over the document, or what do you think? What do you think?
Yeah.
Or I can just give
Give
a
us
TLDR.
the TLDR. You can share the
Um,
document.
sure. Just find it.
I think for many of us, we're particularly interested in what is different from November. Like, what's the delta from
Yeah.
then and now?
Mm-hmm. Okay, let me share my screen. So the delta from then to now, so previously we were talking sort of exclusively about more or less like imposing the constraints of CUDA like graphed callables onto Torch Dynamo, which meant like you have a series of functions and you would like to chain all of their like invocations as a CUDA graph together. And like in that world, we're enforcing one single tape, one single ordering. Like for many models, this is fine. We never graph break. We never take or we never take divergent paths, etc. But it's pretty fragile. So the kind of new just at a high level, and this is in the chat if people want to um, read at their own sort of pace. But so the kind of basic mechanism is we're going to have like there will be two states. Let me step back. So the existing problem is that Dynamo doesn't reuse memory across graph captures. And kind of the big like instance where this leads to memory regressions is when you run the forward, you save a bunch of activations. And if you don't free the activations as you're running the backward and reclaim that memory, you get a large memory regression. And this is what we like saw in inductor, no CUDA graphs for a while until it was fixed. Like I think AOT eager kind of has the same problem, and like its memory compression is like 86% of what like normal is. So you get a big regression if you aren't able to reclaim activations. So we need activations, like we need the forward and backward to reuse the same memory pool. So kind of as it stood in November, we would like run like we would share a memory pool across all of our separate CUDA graph captures, and this would solve this problem of the activations. And like in making this like tape of like recordings of CUDA graphs, we would like add guards that like the order of CUDA graph invocations stayed the same, and like the memory access patterns, et cetera, are the same. But let's go down to, so there's kind of two patterns here, like one, the initial recording where you set up all the CUDA graphs, and then the second where you're just like, now you're in the steady state, you're replaying CUDA graphs. But it's fragile. So like taking this sort of example here, we have we have control flow. So you have this first y equals x times 3, and then we have data dependent control flow. So this will trigger a graph break. So this is one CUDA graph recording, and then let's say we take the second path. So we do this first graph 1, and then graph 2, we record it. Let's say we rerun that path some number of times. And then in the future, we run y equals x times 3, and then we run the second path. So at the point when we get to this second function, all we have done is replayed the CUDA graph state from this first graph. So there's no, like the CUDA caching allocator doesn't have sort of, like there's nothing that's been done to it. All we've done is replayed the graph, like the memory as it is kind of live, as like Y is live, like isn't reflected in the CUDA caching allocator. So kind of naively, there's no way to do a new recording of the second graph in a way that would like ensure that we're not overwriting this other memory that like is currently actually being used. So the new plan is to basically checkpoint the CUDA caching allocator state after every CUDA graph recording, and then make it resumable, which would basically, like when we get to the second path, where we like set the CUDA caching allocator state such that it accounts for all live tensors. That is like midway through our CUDA graph execution. And now that like the memory, the CUDA caching allocator is in a state such that like it can reason about tensors that are live and do correct allocations that don't overwrite existing tensors, we can record more CUDA graph traces from there. So kind of the TLDR is we're building up a like tree of traces of different CUDA graph executions, and we're check joining memory state at each point and finding a way to resume. Ed, go ahead.
Yeah, I mean, I just had a question about this. So
Mhm.
I am trying to remember. So I feel like there was a reason for it, but I don't remember. So I'm going to ask you. So
Mhm.
why do we have to do the tree design? Wouldn't ordinarily we expect the happy path to be we always hit the same like segments in the same order every time we go through the graph? So would it not be possible to just go into some like less optimized state, similar to how like if you have a tracing JIT, if you hit a bailout, you just kick yourself out and go do the normal thing until you get onto the fast path again.
Mhm.
So do we have to do the tree branching structure for CUDA graphs immediately, or is there some reason?
So like one thing to know is like just any recompilation for any reason will trigger like a um let's say we have some dynamo guard that like fails in any sort of way, like that will break the like naive tape. And if we break that naive tape, like CUDA caching allocator like shares separate memory for its private pools, so that memory will not be reused across that other path. So like it would be fine maybe if we hit the unhappy path, whatever, and memory was the same, but actually memory would regress a bunch because you'd be using two separate memory pools. Natalia?
How are you going to checkpoint and resume the state of caching allocator? Like, wouldn't you need to free the allocations that you've made and potentially make the tensors that currently exist in the context invalid? I just don't see how you're going to create this time machine and not break anything else.
So just a little context. So the CUDA caching allocator, when it makes allocations, like it holds on to them forever. So it never frees existing like allocations. So like let's say we've checkpointed our state here, we've run it some number of times, maybe we've made some new allocations. Every block that was allocated at this point will still will be allocated forever. So
Well,
those blocks, yeah, go ahead.
It does free existing allocations when it runs out of memory. So like, you have to at least end your scheme when that happened.
Yeah, I guess we were, yeah, but if we run out of memory, I'll take that as a note and follow up on that. Assuming that's a rare case, those allocations are free forever, are allocated forever, and so like there may be additional allocations, but it like if we've executed some like part of an iteration, then like, I guess one other thing to note is
Actually,
like the
Elias, no, I wanna push back on Natalia's comment. We're talking about when you are doing CUDA graphs, right?
Mhm, mhm,
With CUDA graphs, allocations for CUDA graphs, we indeed never free them until the CUDA
mhm,
graph dies, which
mhm,
for this tape structure, we basically will keep it live forever. So if we still won't free them. I guess we
mhm.
could panic and free all the CUDA graphs in that case, but then, sort of you're just resetting the state and it doesn't matter. Natalia, do you agree with what I just said there?
Yeah.
Voss.
Um,
Yeah, super back to basics comment for me. Why can't we free them? Is that just like a core feature of CUDA graphs that we can't ever change, or is it something we decided? Sorry if that's a silly question.
Yeah,
that's a good question. Oh, go ahead, Natalia.
that's a feature of CUDA graphs. They bake in the addresses to all the arguments into CUDA graphs, so you can never change the memory allocation of your argument.
But to oh, go ahead.
One way I would say it, Buzz, is they bake in the pointer that value directly. So whatever is at that address needs to always be at that address.
Yeah, I understood. That was a good answer. Thank you.
So to back to Natalia's questions, if we're like part of the way through our tape, we will only have live tensors that have been allocated part of the way, like up to that point in the tree execution. So there will be no additional allocations like tensors live other than the ones that are like partway through the execution. And those are exactly the tensors that are like accounted for in our checkpointed state at the CUDA graphs.
What if something happened in between the graph regions?
So in between so I have another section, live tensors between iterations, which we can go over.
Let's go over it.
Okay, so let's say we're benchmarking running inference with the following code. So you're running your ResNet.
Actually,
run
no, I
out.
don't think this is what Natalia is asking about. This is talking about the case where you're like running 2 training loops and it accidentally spills over. But Natalia is talking about a simpler case where you have a graph break, and in the graph break, there are some operations that aren't dynamo captured. But they're still going to access memory from the results of the CUDA graph, and they are also going to allocate memory. So how does that interact?
Yeah, so if they're allocating memory, they won't be allocating memory within the CUDA graph because it's a separate pool from the normal caching allocator. So the only like memory delta that could happen to our checkpointed state between 2 CUDA graph captures is that like memory is no longer needed, and that is like an easy thing to account for in our checkpointed state. You just like whatever blocks were allocated, you can deallocate them. And that's also like accounted for in the other like accounting we're doing just to like check that memory and like memory output of tensors and stuff is stable.
And to ask a follow-on question here, let's say that we do some allocations after the CUDA graph, and then we start a new CUDA graph region. Do I have to do a copy to get those tensors into the CUDA graph pool?
Yeah, so tensors that were not allocated to the pool have to be copied in before running it, which is the same as our current behavior. And also we should be doing a lot less of those copies since we're like now any tensor that has been allocated as an output of a pool doesn't have to be copied in, which is like not the same as it was previously, where like for the backward we had to copy in all the activations, which we won't have to do now.
No, let's wait, but input tensors are not part of the pool. We just keep them alive to make sure that their references don't change, but they're not part of the capture pool. And there is currently no way to copy tensors in the pool.
So the yeah. I don't think there's any reason the inputs like couldn't be part of the pool. Like if you allocate the like copied over inputs and then write to the inputs that are in the pool, like that should be doable. I think that's what I
But
have. I think that's what I have implemented on the PR.
okay, I'll take a look at the PR.
On the first PR, I don't have the delta like the checkpointed state. It's like a work in progress, but the initial like tape version is out.
No, but
So-
the things that are in the pool can only be allocated during the graph capture. There is no
Yeah.
other way to. So, and inputs by definition are created before the graph capture, so they don't end up in the pool.
I do like I like record just the allocation of the inputs in a graph capture just so to like reuse the pool, I believe.
Sorry, what do you mean by you record? Because in general, this is going to be user code that you don't have control. Like it's going to be like some data loader producing an image, right? So unless you go change the data loader to like start the Cuda tape at that point in time, you're not going to have it in the correct spot.
I mean the like the transferring of the non-CUDA graph pool inputs into the CUDA graph pool.
Right. So
like,
so what's going to happen is that when you start a CUDA graph region, you're going to have to copy the inputs into the pool. There's no way around that. But parameters don't have to be moved because we assume those stay fixed. And for graph breaks, as long as you're just referencing tensors that were from the previous CUDA pool allocation, those also don't have to get copied because you know they're in fixed locations.
That's correct.
Any other questions? Elias, anything else you want to talk about? Yes, go ahead.
Like what does this net out to in terms of like a win or a loss on peak memory? Like in the branching example there, I'm guessing kind of depends on what's in the branches, but like, does this usually net out to being a win with CUDA graphs, or does it just depend a ton on the context?
So just the like not being able to use just the using separate pools for every CUDA graph, like we have a bunch of OOMs internally, like we know just the simple case of like not being able to free activations when you're running the backward is like 14% roughly. And then just like the multiple trace case is just like for robustness, so you don't like you can graph break, you can like it's not even just graph breaks, it's also like, oh, we failed a guard and we have to like we have failed some spurious guard and we're rerunning similar code. It's just so that like I think as we're seeing with export, like it's really hard to never have graph breaks or any divergent behavior, and I don't think that's like a particularly robust thing to ship if you know you have one divergent path and you it's not great.
That being said, when you end up with these if I branch the tree, do the two branches of the tree get to use the same like share CUDA memory? What is the word? Yeah. All right, we're still using all the same pool. Is that right?
That's correct.
So the overall usage of a really big tree with lots of branches will be the maximum memory usage for one of the paths through the like overall the paths through the tree. Is that right?
That's correct.
Okay.
Cool. I have no further comments.
Okay, then let's keep rolling. All right, Brian, tell us about our short-term plans for inference mutation, and maybe we can open the discussion for the long-term plan.
Sure. I'll zoom in a bit. Can you all see that? Okay. So I guess the context behind the doc is, so like the current state today is basically that we run AOT autograd. AOT autograd sends some graph to the backend, like inductor, to compile. And there's some like existing handling for input mutations, which is like a thing that can show up in a bunch of random contexts when you compile programs. And the current state today, like the default state, is basically AOT autograd works really hard to ensure that the backend never has to see any mutations, including input mutations. And the way it does that is that basically when we see an input mutation in the graph that Dynamo hands us, AOT autograd basically works to like completely eliminate the input mutation from the graph. And then it runs this opaque epilogue after the compiled graph finishes that basically like reapplies the mutation to the input afterwards. And so that kind of guarantees that like in all cases, backends or compilers like inductor never see mutations. And it can also be like not necessarily optimal for performance because we do this like eager mode copy underscore at the end of the graph that there's no opportunity to kind of like fuse that with anything else. And so the context for this doc is like one other piece of context is basically AOT autograd has two paths today. There's the inference path, and then there's the autograd path where we construct a backward graph. And in the autograd path, we always functionalize everything. And in the inference path, we actually don't functionalize today. And so there's this ongoing PR to try to functionalize in both cases. And one kind of downside of that PR, if we sort of like keep the status quo, is that optimizers are like the main or like a very common source of input mutations and kind of like a vanilla model that you run. And so the hypothesis, which I have started trying to benchmark but don't actually have numbers on yet, is that if we like turn this on, we're going to regress optimizer curve because we're going to start removing all like parameter updates from the graph and like reapply them afterwards. And so like kind of what we want is some way to send input mutations to the compiler. That way they can fuse the input mutations for better perf. So that's kind of the background. Any questions about that before I talk about the doc? Yeah, so I talked to Ed and Natalia and some other people a bunch, and there's like a tentative current plan, and that can totally change depending on what people think, but I'll just kind of go over it. And so I guess first I'll talk about the constraints, which are, you can kind of imagine like supporting mutations in inductor / other compilers will be better for performance because of the reasons here, but it's also kind of hard to do. And there's like a ton of weird edge cases around input mutations. And like the input mutations optimizers are like probably pretty simple. It's kind of the parameter is the input and we add underscore the parameter. And then there's this whole like tail end of edge cases. Like what if you have a graph where you take some weird complex non-contiguous view of the input and then you do a mutation on that view, and like, can we reasonably get good perf by sending that to a compiler? So one thing is sort of like, do we want to send all input mutations to the compiler? Do we just want to send simple ones? Like, does it make sense to have kind of like multiple toggles? And so, yeah, like, do we send all of them or just some of them? That kind of depends on the perf. And also, do we want to have like multiple options depending on what the compiler can support? And so like what we've sort of agreed on so far is that supporting multiple options is pretty complicated, or, you know, we could do that if we need to, but it kind of adds a lot of complexity to AOT autograd. And so we can have a config flag that's just kind of all or nothing. In the inference case, like, do we always send input mutations to the compiler, or do we like always run it in that opaque epilogue? And if we do send input mutations to the compiler, this is kind of the proposal for what that would look like. So there's actually like two ways to send the input mutations to the compiler. So suppose we're given this function or this program where we take an input, we like do multiple mutations to it, and then we return the input. And one option is to like directly send this program to the compiler. Another option is to actually do something like closer to what functionalization does, but still preserving the input. And what that is basically like functionalization will functionalize away all of these mutations, and it does it by doing something like this, where we like take every in-place mutation and we create this like intermediate updated buffer. And And then to quote unquote preserve the input mutation, we can just insert this copy underscore at the end of the graph, which is like actually basically what that opaque epilogue in AOT autograd does today. And the only real difference is we are like directly putting it in the graph instead of eagerly running it as part of this like opaque epilogue. And it's sort of like, what's the difference between sending this graph to inductor versus this graph? So one reason it's sort of easier for inductor to handle is because if you see these two mutations, then you have to worry about what order they run in. And you like, that's this extra thing to worry about. Versus here, like there's only really one mutation at the end, and you can just kind of run it. And then the downside is that we have these extra intermediate buffers that like could live longer than they need to. And so kind of the current thinking is that if inductor can compile this all into one mega kernel, then this shouldn't be significantly worse performance than the first graph. And then the added benefit is that inductor doesn't need to handle just a subset of input mutations. It can kind of handle arbitrarily complicated input mutations just because they all desugar into a giant copy underscore. One other small thing I'll add is that these are all data mutations, like mutating the data on the input. There's also metadata mutations. And at least the current plan is to not bother putting metadata mutations into the graph, just because you can't really get better perf from doing that in a compiler versus eagerly in an epilogue. And it's sort of easier for inductor not to have to worry about it. So yeah, that's basically it.
Well,
yeah, I think you kind of answered this, but so would there ever be a case where there would be multiple copies on the same input, or does functionalization guarantee that there's only one copy writing to a given buffer?
Multiple copies on the same input. So are you talking about the case where you have two inputs that actually are aliased, and then like the graph mutates one of the inputs?
Yeah, I mean, I guess I'm not delusional that I can think of all the cases right now, but just I'm asking if it's guaranteed that there would only be one copy operator that mutates to given input, so that an inductor really doesn't have to care about ordering.
Yeah, that's a good question, and yes, AOT autograd will ensure that the copy underscore never happens to like some. No, wait, I should say that differently. I guess there's no guarantee about that. Yeah, you might call it like inductor might see graph with a copy underscore where the thing that we're mutating like aliases.
I'm gonna butt in here. So today AOT autograd will tally up precisely all of the aliasing relationships for the inputs, right? And if there are multiple inputs that are the same tensor, we convert them into a single input. And if we have multiple views on the same tensor, we create a synthetic base, which gets passed in, right? So I actually do think we have this guarantee that any given output only gets written to once.
Yeah, I have a prototype where I actually don't do that, but we could definitely do that if we need to.
What do you mean by your prototype? So let's just forget about putting them into the graph for a moment and just talk about like because one of the ways to reason about whether or not these graphs are correct is because we just say, well, it's the same thing that the eager mode code would have done. We've just, actually put the copy underscores into the graph or not. So it seems to me that in eager AOT autograd, we shouldn't write to the same tensor multiple times, if only for the reasoning that it's totally useless to write to the same region of memory twice with a copy underscore. So we're doing unnecessary work, and we should avoid doing that if that would have happened.
I would agree with that. So.
I see. I think that's fair. I guess I feel like I can imagine cases where that isn't the optimal thing to do. But maybe like in general, that's still the better thing.
Well, I mean, imagine for us in the group.
Like if you have a, I don't know, make a tensor of size a gigabyte, take 2 tiny slices of it, pass those 2 slices to your program, and then you mutate both slices. then like the optimal thing to be done eagerly is like you just mutate the tiny slices. Versus if you want to turn that into like mutate the giant base, we could do that. You're just like doing a lot more work.
And then I have a question for you, which is, what does AOT autograd do today for this case?
Today, yeah, that's a good question. I am pretty sure it mutates the slices. I can double check that though.
No, but because you have two views which are for the same storage, don't you create a synthetic base for that case?
Yeah, but there's this layering thing. It's like, do we create the synthetic views like before or after we like apply the mutations? And I can't remember. I feel like it's kind of underneath the thing where we apply the mutations. But I can check.
Sherlock?
So we're talking about this problem in the context of supporting buffer mutation and optimizer weight update. So for this kind of things, like it usually tends to happen at the end of graph. So I'm thinking like basically we're saying we need to come up with a simple rule to say like when can we just skip functionalization and simply push such operation to the epilogue part of the graph so that backends can optimize it. So is it like, so like can we think of the program as two-stage, whereas the first part is functional and second one is non-functional and involves buffer mutations? And functionalization can basically analyze the graph to say if the mutation, if there's no read on this buffer after this mutation, then it would be safe to directly put this in the epilogue graph. Basically, like you can only do buffer read first and then do buffer override. And doesn't violate the single assignment assumption in a single step.
I'm curious, Sherlock, where your question is about how do we generate such a function? Is that what you're trying to figure out?
Yeah, like.
Okay. I think the answer is functionalization today already generates that function. We know how to do that.
Yeah, but like it looks like in the Brown's example case, like if there's no read, like after for the input mutation, you can simply skip the functionalization pass and directly push those to the epilogue graph. So you don't need to do functionalization and then copy underscore. You can directly move the add underscore and mount underscore into the epilogue graph.
I think we have a goal though. I think we want those ops in the compiled graph because then the compiler could do more fusions potentially.
Yeah, like basically the epilogue graph will also be passed to the compiler. So basically like the whole program becomes separated in two stages. First part is functional and second part is non-functional and does mutations. Both graphs are passed to inductor in either one graph or joint graph. That's up to us.
Natalia?
Yeah, but that's exactly the gist of this proposal. We never want to skip functionalization because inductor won't be sure how to handle graphs that didn't have functionalization. We are making the mutating graph safer for inductor by explicitly running functionalization on them and only adding copies at the end. Pretty much like functionalization works today, except those copies are also getting sent to inductor, which today they aren't. Does that answer a question?
Yeah, but one thing is that we don't need to send the copy underscore. We can directly send add underscore if we know it is safe.
Yeah, but that's very hard to know. That's the point that we want
Why?
to
like
functionalization.
Actually, yeah, this is what I want to spend the rest of the meeting on. Brian, can I grab the screen?
Yeah.
So I want to see the discussion by talking about a few of the reasons why it is difficult to do things safely, and hopefully that can seed more discussion. So let's just talk about the proposed optimization that Sherlock wants to do. So essentially it's something like we have an input and we do a mutation on the input, and basically Sherlock is like, if there are no more reads, then it is valid to do the mutation here. Is this the optimization you're proposing, Sherlock?
Yep. Yeah.
Okay. So, so I want to dig into the if there are no more reads. Now, obviously, what cases does that work? What cases could violate this? So one is obviously if there is another use of X. That's easy. But here's another one. If there is another use of an alias of X.
It's like we already have the alias map. Right.
Okay. And there's another case, which is if there is another use of the buffer that inductor allocated X to live in, well,
wait, why is inductor in this picture? Like we are talking about graph here, like inductor, it's downstream and it's up to, can make separate decision on how to take care of the buffer given the whole graph.
So let me think.
So basically, like you cannot touch the storage. If you don't touch the storage, you know that it is safe.
Okay, so let's leave these two. Does anyone else in the room have other examples of where there can be reads?
We should just go to GitHub issues and look at the multiple in-place issues that
Sure,
are.
let's look at the multiple in-place issues.
But our busy fathers have really filed at least half a dozen in-place issues where inductor is not doing the right thing, despite its claiming that it can consider some in place.
I guess a related question is, does making it so that inductor only has to accept copy underscore as an op it can lower that's in place, does that simplify the logic in the scheduler at all versus the case where you actually have to support pointwise ops and other kinds of ops that might be in place?
It would simplify the logic if inductor had the logic, but the mere fact that we have those half a dozen in-place issues means that inductor is claiming to do something, and in fact it doesn't.
So here is
Yeah,
an
that makes
example that was recently filed. So the graph in question here is, well, it's pretty complicated. Natalia, did you look into this one in more detail?
I didn't look in detail, but yes, it creates additional tensors that are aliases of some intermediate results, and then modifies one of those aliases.
Yes. But I think Sherlock's argument for this one is we never actually mutate the input in this case. So this is in fact a functional function, and thus Sherlock doesn't mind if we functionalize it because we only need to preserve mutations on inputs. So this one is just functionalization will fix it, and you don't even have a problem with input mutations on this example.
But that also means that functionalization has to be run on this. Do we want complicated rules on when we want to run functionalization versus
so
when we don't?
let me modify Sherlock's proposal, right? So Sherlock's proposal was like, well, if I have an x.add here, and then like I'm like, oh, it never gets used again, then I'm going to keep the add underscore. So let me give a counter proposal that is compatible with running functionalization. So step 1, run functionalization. 2, for each copy underscore, move it to the earliest point in the graph where the input in question no longer is red. So let's just do an example. So let's say that I have x, y, and I've already done functionalization. So I have a new x and a new y. Actually, this is bad, and then I have x copy underscore new x and y copy underscore new y. The proposal here is essentially that if, for example, the computation for new y doesn't no access to x, doesn't access x, then I can float this copy up. Sherlock, does this feel like as good as your original proposal, where you said if we, don't read the x anymore, we can do the mutation immediately? Or is this worse? Does this feel worse to you?
Like, my point is, like, we don't need to use copy underscore here. Like,
well, okay, but remember, inductor is involved. So let's suppose that this was indeed x plus 2, right? Which is equivalent to the x add underscore 2 here. If I have this code in inductor, I believe, well, I don't know. Natalia, does inductor generate good code for this?
For this single input mutation, yes, it does. For some more complicated cases, it doesn't, but it also doesn't generate good code when there are in place cells, because there is just some bug in it. It's not a law of nature.
But wouldn't it be easier for inductor to generate like x
No,
add underscore?
it's like barring the bug that exists today, it should be absolutely the same whether to generate add underscore or add underscore. Compilers are created to free people from writing their code just so they can naturally express themselves, and compiler will figure it out.
No, like, but
within
the
limits.
add underscore here is not in the middle of the graph. Like, the add underscore is always at the end of the computation for any for any of your scheduling.
No, it's not necessarily the end of the computation. Even in the optimizer codes, we are first updating some momentums and buffers, and then we are updating parameters with add underscore. So there are a bunch of underscore operations flying around. They are applied to things that could be thought of as graph outputs, but not necessarily.
Are there any other questions from other folks in the room? Has the conversation been making sense, Brian?
Yeah. I guess one question I have is, do we think, like, I can understand the moving the copy underscores earlier in the graph as being a thing that we can reasonably do. Do we expect it to be useful? Like, in the case where inductor generates one kernel, it probably doesn't matter. Is this something we think is potentially useful for inductor or potentially useful for export, or maybe both?
So
we are talking about this thing mostly in the context of optimizers. If inductor is freed of its bugs, the kernel should be just a single kernel for optimizers. So in that sense, it doesn't really matter where a copy is. Intermediate state where inductor is doing imperfect fusion, yes, it might matter. But the fix for this is not to move copies around, but to fix things so that a single kernel is generated.
There's another situation, though, I'm thinking of, which is if we have a forward, backward optimizer consolidated graph, you might imagine wanting to float the optimizer updates as early as possible so you can get rid of the grads. This is one of the optimizations that is done in the distributed setting.
In the functional world, what happens if you modify an input in place but you never return it? We still do exactly these features. We never return.
Basically the same. Yeah. So what'll happen is, like, the compile graph will end up returning that updated input.
And then we copy it.
And then we copy underscore. Yeah.
So potentially that is a memory efficiency issue.
Yeah, it's also a memory efficiency game.
Interesting. Okay.
One more thing that I want to say is it's actually not so easy to compile the kernels with mutating writes in them, right? Because so another example is the restrict bug, which I don't remember the bug number of. But essentially the problem was it's easier to write code gen where you're like, well, the output doesn't alias with any of my inputs. And when you have these copy underscores that you're trying to fuse together into a single kernel, that makes your life harder because you can't assume that. And you have to like be careful about like restrict annotations if you were doing it in CPU, or just generally like scheduling what order you do the writes, because you need to be careful not to clobber things that you're going to use later.
How many of our bugs have been on CPU versus Cuda? Just because, like, I don't know, like we're gonna have like, it seems. I know we've had bugs, but it seems like I don't know if it's worth saying like inductor isn't going to support in-place ops instead of just like fixing the bugs that we do have. Especially as like, I don't know, who knows what future constraints we have, or like external ops which we want to like trace through and kernel and CUDA, which might have like in-place mutations. Like there definitely are, like, you know, there may be some big bugs today, but like there's a lot of logic in inductor to handle in place, and I don't know if it's really so far from being like fully robust.
But why would we want this logic in multiple places, in functionalization path and in inductor? Like we are working on functionalization to be always correct, so that backends, inductor included, don't have to think about it.
I mean, we have a few like already with like in place the optimizer is like already an example where it's useful to handle mutation. Similarly, like any external op which we want to like support, which might be mutating, and like also because it's an external op may not have the same like functional equivalent, like would also be useful to support.
But we want to support it by sending it to functionalization first and then adding the final copies to the compiled graph. The claim is that it will recover the performance of actual in-place operations very closely.
Yeah, and for like external ops, that's like not really clear how that's going to work. And like we talked in, like, I don't know, Brian was talking to someone who had some crazy like in place backwards gradient. Like, I don't know, I'm not, for like external ops at least it's less clear.
But external ops doing in-place modifications, we can, if we don't have visibility into them, then we cannot guarantee what will come out of it. And if we do have visibility on them, then we could just as well run functionalization and copy. That's what we do today.
In what sense would we not have like visibility? Like we, yeah.
Like if it's, I guess if it's just a black box that we are breaking on, then we want code gen and whatever in place they have will be theirs. For everything else, I don't see why we should skip functionalization. If we don't trust our functionalization, then how do we run it on everything else except inference graphs?
Okay, we are out of time. It seems like there's going to be an ongoing discussion in Inductor about how much mutation to support. But if Natalia says we are not going to do lots of mutation in Inductor, then that's sort of what the story is going to be. So you have to convince Natalia or Jason.
No, I'm happy to do mutations, but today, as those bugs attest, we don't do it right. And I don't know if the correct strategy is to have two paths doing essentially the same thing in functionalization and in Inductor, or just reuse functionalization wherever you can. I am, as you see, heavily leaning towards the second.
Okay. Well, thanks everyone. See you all next week.